Yes, so last time we were discussing this question before we left. It was incomplete. Okay, we were supposed to determine the temperature at the exit, the maximum temperature in the cycle. Then the compressor work input we have determined already. Okay, so then the rate of heat supply to the cycle from the combustion chamber. Okay, so we are at the B part. Now, let us recapitulate what we did. See, this is the overview of the cycle. This is the ideal Brayton cycle, right? So we have two compressors and two turbines in this situation. Okay, so since the isentropic efficiency for the compressors and the isentropic efficiency for the turbine are given, so it means we have to consider them in their calculation, right? So that's why we have state 1 goes to 2A, and then we have 2S. And then similarly, we have 4A and 4S. And then for the turbine, we have 5, and then 6A, 6S, and 6A. Okay, so these are with respect to the isentropic situations. Okay, so now the next thing is to determine the turbine work input. Okay, so which I think we have already determined. Yes, this was the value for the turbine work output. So that was 63.78 kilowatts. All right, so we said that since the turbines have the same isentropic efficiencies, so there is no need, if you calculate for 1, you only need to multiply by 2. So now to determine the rate of heat supply to the cycle, okay, so rate of heat okay, supply to the cycle. Okay, this can be, so I've already defined it from here, but another equation can also be calculated from here, that Q in equals to Q combustion. Okay, Q combustion. This is Q combustion. It can be represented by Q. So these are Q dots. Q combustion, CC. This equals to the combustion efficiency. The combustion efficiency, which is given by CC, okay, times the mass flow rate. Mass flow rate of what? Of the fuel. And then times the calorific heating value. Calorific heating value. Okay, so this is one way in which we can determine the work or the heat input to the system. Okay, so the calorific heating value. All right, so now, as far as Qin is concerned, we know the combustion efficiency. Okay, let's see. Combustion efficiency. This is the mass flow rate of the fuel. Combustion efficiency is given 82%, and mass flow rate of the fuel is given. And we know the calorific heating value. So these are the three components which is necessary for us to determine the what? The, what do you call it? The Q in. Okay, so take note that over here, this is 2.5 grams per second. So it has to be converted into what? Kilogram per second. Means we need to divide by 1,000. Okay, so we can have it like this. Okay, so my Q in It's nothing equals to the combustion efficiency, which is 0.82 times the mass flow rate of the fuel. So 2.5 times 10 raised to the power minus 3 kilogram per second. Then finally times the calorific heating value. This is 55. Okay, I'll make it kilojoules. Instead of megajoules per kilogram, it's going to be kilojoules per kilogram. Okay, times 10 raised to the power 3. Okay, so if you calculate this carefully, the resulting Q in becomes 112.75 kilowatts. Okay, so that's the amount of heat added to the cycle. Now, to determine the maximum temperature, okay, so to determine the maximum temperature in this, I've told you that we could also use this to determine the Q in, okay, but this is a very, very long method. It is simply given by Q, okay, 45 means the heat added from state 4A up to state 5, plus the heat added from state 6A up to 7, and then the heat added from 8A up to 9. Okay, so these are the amount of heat. This is the primary heat. Primary heat that is added to the cycle is this. Okay, and these are the reheating side. So these are the reheating. Okay. So now the next question is to determine, now we have found the rate of heat supply from the combustion chamber. Now we want to determine the maximum temperature in the cycle. So where do we have the maximum temperature in the cycle? Can anyone guess? The maximum temperature in the cycle from this TS diagram is naturally going to be either T5 or T7 or T9. Okay, so if you are able to find any of this, then that gives you the maximum, temperature in the cycle. Okay, so now let's see. We can say like this, that from given that, is number 3, maximum temperature in the cycle. This could be given by, so from Q in equals to mass flow rate, specific heat capacity, okay, T5 minus T4A. Okay, so this is one way in which we can determine T5. Okay, so what we need to do is that, and be careful over here. So somebody will ask, how did you come across this equation? So the heat added, okay, from state 4A, the heat added to the cycle from state 4A up to state 5, okay, that is given by this. And it is nothing, it is equal to the change in enthalpy between the two states. So that gives us H5, and let me see, mass flow rate. It gives us So that gives us mass flow rate into bracket H5 minus H4A. Okay? But like I've told you, the enthalpy of any ideal gas is the specific heat capacity times the temperature. So this simply gives me Q in is nothing equals to mass flow rate, okay, of the gas times specific heat capacity, and then times T5 minus T4A. But we know this Q in already. What is Q in? Q in is given by this. Where is it? Yes. Okay, 11.2.75. That is our Q in. So from this, and then we have also, I think we have calculated T4A. Let's see over here. So our T4A, so this is T2, okay, so T2A is that. And then, yes, so be careful over here. Now, T2A is the same as T4A. So how is it like that? You see, the temperature at this state is the same as the temperature exit because of what? They have the same compression ratio. If they are the same compression ratio, the temperature at the inlet over here, state 1, will be the same as the temperature at the inlet at state 3. Similarly, the exit temperatures are going to remain the same for both compressors. Okay, so therefore we conclude that T2A is the same as T4A. All right. So from here, we will have 112.75 equals to, so kilowatt equals to mass flow rate. Mass flow rate of the fluid is given, you know the mass flow rate, 0.185, 185 times the Cp for air. Okay, so we have, let's say, mass flow rate 0.185 kilogram per second times 1.005 kilogram per second. Sorry, kilojoules. So it should be, this should be kilojoules. Kilojoules per kilogram per Kelvin. And then times, we will have T5. Okay, so here we are interested in T5. So that gives me T5 minus T4A. So T4A is the same as T2A. And then that gives us, let's see over here, 471.3. So minus 471.53. Okay, Kelvin. So from this equation now, we can deduce that T5 is nothing equals to, that gives us 1077.96 Kelvin. Okay, so this is the, now this temperature, T5 is the same as T7, is the same as T9. Why is it so? Because of the fact that all the turbines that we have in the cycle, they have the same pressure ratio. Okay. Now, the next question is to determine the maximum, the total turbine work output. All right, so how do we determine total turbine work output? The total turbine work output is given by, let's see, W total, okay, for the turbine. It's nothing. This gives us the work done by turbine number 1. Okay, so I'll say W turbine number 1 plus W turbine number 2 plus W turbine number 3. Turbine number 3. And they have the same pressure ratio. Okay, so it means if you consider the first turbine, okay, since all turbines, okay, have the same pressure ratio, this implies that WT1 equals to WT2 equals to WT3. All right, so if you calculate for 1, then you just multiply by 3, then that gives you the total turbine work output. Okay, so let's consider turbine number 1. Consider turbine number 1. That's the high pressure turbine. Turbine number 1. So which is given by this. See? So this is the expansion from state 5 up to state 6. Okay, so state 5 up to state 6. But be careful over here. You see, maybe we need to redraw that diagram for us to appreciate what we are doing over here. See, the whole cycle again can be put together like this. We have the TS diagram. For the whole cycle. Okay, so we have, this is compressor number 1. Okay, so we have the isentropic compression. Okay, so this is the actual compression. And this again. So then it goes like this. So then we have isentropic expansion, the first turbine. And then again, it goes like this. Second turbine also, expansion, then followed by the last turbine. And then we have isentropic expansion. Then the fluid is cooled down to its original state. Okay, so here we have state 1. Okay, so this is 2S, 2A, and this gives me 4S, 4A. So this is state 4. This gives me 5, 6S, then we will have 6A. And we will have over here 7, 7S, 7A. And then we have 8 over here. And finally, we have 10A. and this is 10S. Okay, so be careful over here. We are only interested in the work output. This W, turbine number 1A, turbine number 1A. Okay, so the work output from here. So now this gives me so this gives me, we will have W turbine number 1A equals to mass flow rate, okay, of the fluid times specific heat capacity of the air times T5 minus T6A. Okay, so it means we need to determine T6A. Mass flow rate we know already. Okay, so the mass flow rate of the fluid is known, but we don't know the temperature at state 6A. So we need to determine that. Okay, how do we determine this temperature? We have to use isentropic efficiency for the turbine. Okay, so in order to find 6A, or sorry, T6A, okay, so we have to use isentropic efficiency. So isentropic efficiency for turbine number 1 equals to the change in enthalpy. So that gives us H5 minus H6A divided by H. Again, that gives us H5 again minus HS. It's 6A, 6S. Okay, so this can be written in the form of T5 minus T6A divided by T5 minus T6S. Now, we know from the question that this isentropic efficiency for the turbine is given already. Let's see. Yes, isentropic efficiency for the turbine is 90%. And this is applicable for all the turbines. Okay. So this is a 0.9. So now we need to find let's say T6A. Okay. So this is not known. We also don't know T6S. So we need to find T6S and then substitute into this equation. So means we have to consider states 5 to 6S. 5 to 6S. That is isentropic what? Expansion. Isentropic expansion. All right. So if it is isentropic expansion, it implies that T6S divided by maybe I should move to the next slide. So we'll have T6S equals to, or divided by T5 equals to the whole of this equation, 1 divided by square root, sorry, cube root of R, okay, for RP, okay, for the turbine. Overall, I'll say overall. Okay, so all raised to the power. I think I should come clear with, let me derive it for you, so then it becomes clear instead. Okay, so now take note that from state 5 to 6, X, we can have, let's say, P5, okay, P5 over P6, S equals to V6S divided by V5 all raised to the power K equals to T5 divided by T6S all raised to the power K divided by K minus 1. All right. So here, basically, the volume cannot help us. So we are going to adopt these two equations. Okay. So now we will have P5 over P6S, okay, is equal to T5 over T6S, all raised to the power K minus 1. So I'll multiply this by K minus 1 divided by K. I'll do the same thing to this, K minus 1 divided by K. So eventually I will have T5 divided by T6S is nothing equals to P5 divided by P6S. Okay. All raised to the power K minus 1 divided by K. So we are interested in T6. So here we can say T6S equals to P6S divided by P5 all raised to the power K minus 1 divided by K times T5. Okay. Now, we need to determine P6 over P5. But we are told in the question, be careful over here, again, that the overall, we are told in the question that the overall efficiency, let me see over here, overall pressure ratio, yes, equals to 16. Now, this overall pressure ratio is applicable for both compressor and the turbine. Okay, so now assuming we have only one turbine, okay, so let me define this. If I have a turbine over here, in which I have a fluid entry with P1, and the fluid is leaving P2. So pressure ratio for the turbine is nothing equals to P1 divided by P2. Okay, that is it. So again, if we are told that the overall pressure ratio for turbine overall pressure ratio for turbine equals to 16. So this implies that P5 over P, let's see, over P, yes, P5 over P10, okay, P10S, P10, P10, P5 over P10 equals to 16. But how do we determine if I want to find P5 over P6? Okay, so P5 divided by P6 is not given. Neither P7 divided by, oh, what I did here was wrong. So we have 6, 7, this should be 8, 8. And then we have 9 over here, and then 10. Okay, so means, let me sketch the whole thing here for you to, again, understand what we are doing. So we have okay, like this. Okay, so we focus our attention over here. This is 5, 6, 7, 8, 9, and 10. Okay, so overall pressure ratio from 5 up to 10 is given by 16. So if I want to find how do I get P5 divided by P6, how do I get this? Okay, so that's the next thing we need to know. Now, P, from this diagram, I can say that P5 divided by P10 is the same as, okay, P, that gives me P, let's see, over here, P5 divided by P7, okay, divided by divided by P6, divided by P6, yes, times P7 divided by P8 times P9 divided by P10. Okay, so one thing you should know, this state 6 and 7, they are on the same constant pressure line. Means P6 equals to P7. Similarly, P8 is the same as P9. So it means I can easily cancel this. I can cancel this out, and then again I'll get P5 divided by P10. Okay, so now let us see. Now again, let me go back. P5 divided by P10 equals to P5 divided by P6 times P7 divided by P8 times P9 divided by P10. All right. So now, since these pressure ratios are the same, okay, so we assume that P5 over P6 is the same as P7 divided by P8, which is the same as P9 divided by P10. All right. So it means that if we represent any of these by x, x, this is also x. So it means that I'll have P5, which is overall pressure ratio, over P10 equals to 16. And this equals to x raised to the power what? 3. Okay, because this is 3 times x, sorry, x times x times x. So eventually, x, which is the same as P5 over P6 equals to cube root of what? 16. Okay, so now we know the pressure ratio for the individual is equal to the cube root of 16. All right, so now from this equation, what is it? From this equation now, let's see. Yes, from this equation, we can easily determine the T6. All right? We can easily find T6. So this gives me, I'll have T6S. So let me rewrite this equation. TS6X. So we have T6S equals to P6S over P5. P6S over P5, all raised to the power K minus 1 divided by K. So K minus 1 divided by K times T what? T5. Yes. So that is it. So now we know already that P5 over P6, so P5 bet P5 over P6 is equal to cube root of what? 16. So I can make that substitution into this equation. All right. And so this gives me 1 over, if I'm looking for P6S, so I can put S, so it's the same thing. If you say P6S is the same as P6, because they are the same pressure line. Okay, so same pressure line. Okay, so like this. Or P6A is the same thing. Okay, so if I write P6S divided by P5, this gives me 1 over cube root of 16. Okay, so eventually I'll have T6S equals to 1 over cube root of 16 all raised to the power. Now K equals to 1.4. So here I'll have 0.4 divided by 1.4 times T5. All right, so T5 we know to be 1077.96 Kelvin. Okay, so from here, T6S is nothing is equal to 827.798, okay, Kelvin. Okay, so this is the temperature and the isentropic section at state 6S. Okay, so now from here we can use this temperature to determine T8, T5, T6A. Okay, so here we are interested in, watch out carefully, we are interested in this, T6A. We know T6S already, T5 is also known already. So eventually we'll have from isentropic efficiency of the turbine equals to T5 minus T6A divided by T6A divided by T5 minus T6S. This equals to 0.82. Okay. Now, let's see. Oh, sorry, that's 0.9. So this gives me 0.9. And then from here, if you substitute all the parameters, T6A equals to 1077.96 minus 0.9, 0.9, 1077.96 minus 827 minus 0.8. Okay, so T6A equals to 852.816 Kelvin. Okay, so see, this type of questions sometimes is boring and it takes too much time. So, but you need to be very extra careful. You need to take your time. Otherwise, if you make mistake on one side, then it is going to affect all other areas like this. So one has to be very, very careful. Okay. So now we can easily determine the work input to the turbine. Okay, now we know this is A. So W for turbine number 1. So W, turbine number 1. Okay, I'll say turbine A. So this gives me, or I will say the total turbine work input. Okay, so let's see over here. So this gives me M times Cp into bracket T5 minus T6A. Okay, so, but the total turbine, okay, total turbine equals to W T1 plus W T2 plus W T3. But W T1, T2, T3 are the same. So this gives me 3 times M CP T5 minus T6. Okay, so now I will have 3 times mass flow rate, 0.186 kilogram per second, times specific heat capacity, 1.005 kilojoules per kilogram per Kelvin. All right? Then times the temperature difference. So we have 1077.96 minus what? 852.816. Okay, Kelvin. So if you calculate this carefully, eventually the result is W for the turbine is nothing. It's 126.26 kilowatt. All right. So now finally, to determine the, let's see, what is the next question? Yes, the network output. Okay, so that is E, the network output of the cycle. Okay, so but again, network output equals to the total turbine work output minus the compressor work input. Okay, and then we need to determine the thermal efficiency like this. Okay, so now the network, so network equals to W net. This equals to the turbine work output minus the total compressor work. Okay, so compressor work output. Okay, so the total, I'll say total turbine and total compressor total. Okay, so this gives me 126.26 minus 63.78. So this gives me how much? 62.48 kilowatt. Okay, finally, before we end this question, we will have the thermal efficiency. So thermal efficiency of the cycle. Thermal efficiency is the W net divided by Q in, or Q in total. All right. So I've told you Q in total. This gives us Q in total equals to Q 4 to 5 plus the reheat, Q, 2 times Q reheating. Okay, so that is the Q total. So now, how do we determine Q reheat? We have 2 reheats. Look over here. This is after the expansion in the first turbine, then there is reheating. Again, expansion in the second turbine, then again there is another reheating. So there is Q in over here. There is another Q in at this section. Okay. So that corresponds to Q67 plus Q89. Okay. So, but they are the same. Okay. So we need to determine the Q reheating. Okay. So Q reheat equals to mass flow rate, specific heat capacity, T7 minus T6A. All the time it is with respect to the actual cycle, this state A. Okay, so now we'll have 0.186 times Cp, this is kilogram per second, times Cp, 1.005 kilojoules per kilogram per Kelvin, times T7. T7 we have calculated 1077.96 minus 852.816. 816. So now this gives the overall reheating gives 42.09 kilowatt. Okay, so now thermal efficiency equals to 62 W net, 62.48, all divided by so Q in. So we have 11, 2, all right, 0.75 plus 2, 42.09. Okay, so if you calculate this carefully, you get 0.3173. So which is approximately 31.73%. Okay, so this is at the end to this particular question. Okay, so is there any question so far from any of you? Let's see. Okay, so is there any question so far from anybody related to the solution?
No, sir.
Okay, so probably I'll move to maybe another question. Let me see. Okay. Maybe we'll look at the steam cycle, steam power cycle question. So let me upload that one also. Okay, so we have another question here. Yes, so this is a steam power cycle question, and we will try to look at it and see how best we can solve it. Okay, here we are told that consider a steam power plant that operates on the ideal Rankine cycle. Okay, so it's a steam power cycle. The steam enters the high pressure turbine at 7 megapascal, okay, and 550 degrees Celsius, and leaves as saturated vapor. The steam is then reheated, okay, to 500 degrees Celsius before it expands through a low pressure turbine to the condenser. Heat is transferred to the steam in the boiler at a rate of 55 megawatts. Okay, so then the steam is cooled in the condenser at a pressure, operating pressure of 50 kilopascal by the cooling water from cooling tower, which enter the condenser at 26 degrees Celsius. Show the cycle on a TS diagram with respect to saturation lines. And by assuming the specific heat to for cooling water is 4.18 kilojoules per kilogram per Kelvin, determine the specific enthalpy for all the 6 states. So here we need to sketch both the TS diagram and then also the flow chart or the flow. Okay, so if you look carefully, so we have, this is the boiler, I would say, of the turbine, of the steam power cycle. And then the steam enters a high pressure turbine. First, it is expanded Okay, it expands and reheated, and then goes back again to another turbine. Okay, that's the low pressure turbine. Okay, this is the low pressure turbine. Before the fluid is expanded again into the condenser. So we'll say this is our pump. Okay, the pump is this. The fluid goes into the condenser. Okay, like this. So if we name this inlet to the pump to be our state 1, this is state 2. Now state 3 is going to be this. This is going to be state 4. Okay, and state 5 is this. State 6 is finally that. Okay, so we can establish that P, see, we are to consider a steam power plant that operates on an ideal reheat cycle. The steam enters the high pressure turbine at, okay, so means P3 equals to 7 megapascal. T3 similarly 550 degrees Celsius, and leaves as saturated vapor. Okay, so it leaves, so state 4 is equal to saturated vapor. Okay, and then the steam is then reheated to 500 degrees Celsius. So means T5 equals to 500 degrees Celsius. Okay, heat is transferred to the steam in the boiler at a rate of, so means here we have Q in equals to 55 megawatt. All right, so 5:30, then we will stop and continue again some other time. Okay, so let's see over here. Now we are told the steam is, so the steam the steam is cooled in the condenser at a pressure of 50 kilopascal. So it means that the operating pressure, okay, P6 equals to P1 equals to 50 kPa, kilopascal. Okay, so the cooling water enters the condenser at, so we have cooling water from here. It enters and then it leaves. This is the cooling water. Cooling water. So the temperature inlet for cooling water equals to 28 degrees Celsius. Okay. So the temperature inlet for cooling water is 28 degrees Celsius. Okay. Now, show the process on a TS diagram with respect to saturation line. So TS diagram looks like this. On a TS diagram, we have a situation like this. Okay. So in which we have this low pressure line and my high pressure line is given by this. Okay, so then I have reheating. So there will be expansion. So expansion over here up to this state. And then there will be reheating. So this is just a sketch. Reheating up to this state. Okay, so we have the fluid is pumped into from the pump from state 1 up to state 2. And then we have state 3, 4, 5, and 6. So this is just, what do you call it? A rough estimation about the state points. So we will determine the exact state points in the calculation. You understand? So this is just, so in the end, we have to maybe come back and correct the diagram, depending on state 1, state 2, what are the properties of the fluid. Okay, but now the question says, determine the specific enthalpy at all states. All right. So first, we need to find the enthalpy at state 1. At state 1, what do we know? The pressure here, P6, constant pressure. P6 equals to P1. All right? So P6 equals to P1. And this equals to 50 kilopascal. And again, be careful. We are told steam is cooled in the condenser at a pressure of this, okay, by the cooling water from cooling tower, which enters the condenser at 28 degrees Celsius. Now, for every power plant, state 1 or steam power cycle, maybe I should draw this clearly for you to see. So okay, so let's assume this is the drawing, and then we have this. So this is state 1, this is state 2. And then we have this this is the reheating, and then we have this. Okay, so this is state 3, 4, 5, and 6. So for every steam power cycle, this particular state is saturated what? Liquid. So it means that if state 1 is saturated liquid, then this implies H1 equals to HF at the given what? Pressure. Okay, so at a given pressure, that as 50 kilopascal. And if you check properly from the property table, this gives us 340.5 kilojoules per kilogram. And similarly, specific volume equals to VF at 50 kilopascal, which equals to 0.001030 meter cube per kilogram. Okay, so I think we will stop over here. And next time we are going to look for state 2, the properties at state 2. Okay, so it is very easy. I've already told you last time that if you know the work done by the pump, so W for the pump equals to H2 minus H1. Okay, that's the work input to the pump. Because we need a pump to pump the fluid from state 1 to state 2. So from here, H2 will give us W for the pump plus H1. Okay, so if you know WP, just add it to H1, then you can get H2. That's the easiest way to determine H2. Okay, so maybe next time we will first determine W2, or maybe we should just do that and then finish with state 2, and next time we will move to state 3. Okay, so we can say that process 1 to 2. 1 to 2 is isentropic compression, isentropic work in the pump. Okay, so now WP equals to, if you remember this equation, P2 minus P1. All right, so W gives me 0.001030. Now, the pressures are given. We know the high pressure line and low pressure line. Here, P equals to 7 megapascal. And here, P equals to 50 kilopascal. So this gives me, let's see over here. So this is the specific volume, 7,000 minus 50. So this gives me 7.1585 kilojoules per kilogram. Okay, so if you know WP now, you can easily find H2. So now H2 which is state 2, equals to WP, which is 7.1585 plus H1, 340.54. So therefore, H2 equals to 347.6985 kilojoules per kilogram. Okay, so this is the value for state H2. So next time when we will meet, we will consider state 3. Okay, so I will stop over here. If there is any question, please let me know. Okay, is there any question so far? Okay, so I think there is no question.